Alrighty. Get going to the big board here. Alright, hello, good afternoon / evening to everybody here. Thank you very much for coming on out here to the stream again. Welcome back to Math 126, some business calculus. Good to see everybody coming on out here. How's everybody today? Hopefully everybody is doing absolutely fantastic. Hopefully we're ready for another day, another day of some rip-roaring mathematics. Used to hope so anyway. You never know. Hopefully everybody has. Hopefully we're gonna get a trickle in full of people. So hopefully we'll have some join us fairly soon. People who are here, I hope you're doing very well here. Got a few things on the agenda here for today. So see if we can get a few things done here for now. I'm gonna do some more derivative stuff here today for sure. So at least we're gonna do a lot of different type of examples here. So certainly that will be. I felt we got a little bit of practice here last time, but hopefully we'll have get a little bit more here for today. You've been working on the homework and stuff. Hopefully you've been working on that and the test stuff. Or hopefully, in all cases, hopefully you've been having fun this summer. That's one thing I can hope. Very least. Very good, very good. Alright. We're going to get started here in roughly about 3 minutes with class. And then we'll go ahead and so easy enough. Okay. I see a few people in here already, so hopefully, maybe they're watching the ads right now. You have to watch the minute or two worth of ads that everybody has to go through. Wait here about another couple minutes here, and then we'll get started. What do we do now? Check Probably check that. Oh, wouldn't be so bad. I did that yesterday. That's you don't work. Okay. All right. All right. Okay. Okay, so gonna go ahead and get going here. It's 6 o'clock, so we'll go ahead and get started here. All right. Hopefully, happy to see everyone today. All right. Go and get started here. We'll do some intros and we'll get right into. Hey, Lee Wen, good to see you. Hopefully, you're doing really well here today, Lee Wen. You're the first one to respond to me. I'm like, I know there's people in here, but good morning at 6 p.m. Hey, did you just wake up, Elizabeth? Is that what happened? You just wake up, you're like, I wish. It's like, wake up at 5 p.m., get ready for a class at 6. Okay, yeah, that's fine. I was worried nobody would respond to me. I'm like, I just feel like I'm talking to myself all the time. I mean, I don't mind, but that's what Friday nights are for. Got that right. This Friday I'm going to be pretty busy, but I'll be hosting a friend for a bit. But yeah, good to see you too. I was worried again. I was worried because like nobody was saying anything, and I'm like, man, this is kind of lonely. I was like, I know you're there, but why don't you respond to me? You have to treat me so cold. Okay. All right. All right. Let's do some intros here. We'll go ahead and get started. All right. Okay, let's get started today. Welcome back to Tuesday. All right, so today we're going to pick up where we left off last time. Last time we talked about the end of chapter 2, did a little bit of stuff here with talking about the derivative, talked about how to find the slope of a tangent line. All right, today I want to continue moving forward here into talking about derivatives. Okay, I want to practice it a little bit more here because I felt kind of last time here we're a little bit shaky here with derivatives, but I figured we could get a few more looks here about how to do some of these problems here. I figured once we do go ahead and do a couple more examples here, I think that should shore up a few things that we'll be doing here today. We're also going to be looking at a few new rules here for derivatives. So today that's on the agenda. So we're going to see how we apply that and of course applications to go along with that as well. All right. In any case, let's go ahead and go to the big board here. Let's take a gander and let's see what. All right. Okay. So I brought up the book here. Again, we're going to take a look at one of the problems, maybe one or two of these problems here, so to kind of showcase what we want to have happen. All right. So I'm going to start off here with number 23. So let's do 20. Actually, no, I'll do 24, actually. So 24 sounds like a better plan. So let's do 24 here. We're going to find this derivative. All right. So here we have f of x is equal to x to the third plus 2x squared plus x minus 1. And this is all over x. Okay, so we have this problem of here of which to start with. Now, in order to tackle this problem here appropriately, all right, what we need to do here first is we need to go ahead and rewrite this problem in something that's a little bit more manageable. Now, in order for us to do that here, what's the trick behind this problem? The trick is that we're putting this all over x, which means that we can basically break this up into individual fractions. We can divide every term we see here in the numerator by that single denominator of x. Meaning to say we could have, we could rewrite it as x to the third over x plus 2x squared over x plus x over x plus 1 over x. Okay, so we can certainly write it this way. We're just going to split it apart into many different fractions here, again with all the same denominator. And then we could go ahead and simplify. So simplifying here, we get x to the third over x. That means one of the x's cancels out. So that leaves us with x squared. 2x squared, again, 1x cancels out. That leaves us with 2x. X over x is just going to be 1. Okay, so just 1, x divided by x. All right, and then finally, we have 1 over x here. Remember that 1 over x here can be rewritten as x to the minus 1 power, right? That's something that we talked about here last time. One of the rules we discussed, it says, okay, put something over x, we can just move that to the numerator, and that becomes x to the minus 1 power as a result. Okay, so now we want to go ahead and find the derivative of this function here after doing some of that simplification. So can anybody tell me here, what is the derivative of this particular function of x squared plus 2x plus 1 plus x to the minus 1? What is that derivative going to be? Hey, tell me here, what is the derivative of what you see here on the screen? That down just like so. Guys, what do you guys think? It's the derivative of x squared plus 2x plus 1 plus x to the minus 1. Again, don't forget the power rule that we talked about here yesterday. That's going to be something that we are going to use here. If you need a friendly reminder about that, let's go back to that guy right there. And the power rule here, something we talked about, is again n times x to the n minus 1. So this says 2x plus 2 minus x to the minus 2. Okay, that is correct. Very good. So x squared here, the derivative of x squared will be 2x. That's correct. The derivative of 2x is just 2. Okay, so that's fine. And the derivative of 1, we talked about that last time, is just going to be 0. Okay, so effectively will cancel itself out. And then finally, we have x to the minus 1. Bring that minus 1 out here to the left. That'll become minus x. And then we have x to the minus 1, so that'll be minus 2 there as our result. Good. All right, so that's correct there. Very nice, both of you. Wonderful job. Okay, so we have that. And that's all well and good. All right. Any questions about that so far? Again, hopefully that just kind of gives you a friendly reminder about what we discussed here yesterday. You're just having a slightly different look about how to rewrite our problem to make it easier on ourselves to go ahead and approach these derivatives. So having this kind of thinking is like saying, "Hey, let's rewrite it into something easier." That's the kind of mindset I would like you to have once we go ahead and do these type of problems here. So, any questions at all before we move on? Any questions? Again, you can ask a question or just type no in the chat, and then I'll go ahead and move forward. All right. And by the way, if I'm going too fast or anything like that, just again, please stop me and ask a question, okay? So don't feel like you have to be falling behind. All right. Please ask a question if you have any. All right. Let's take a look here at another problem. Okay. Now this problem here is going to be slightly a bit different. Let's talk about this problem here. So the next problem I want to focus on here from the book is going to be something that we had actually discussed a little bit here yesterday, but didn't really expand upon, and that is the equation of a tangent line. So that's going to be here. We're going to do one of these problems for sure. So go ahead and met that out here in a second. But let's take a look at the step-by-step, blow-by-blow analysis here about how to find the equation of a tangent line. So we're basically going to start here with number 4 from the 3.1, 3.2 handout, and we'll see exactly what we get here. All right. So number 4 says, how do we find the equation of a tangent line to a graph of a function at a specified point? So there's going to be a 4-step process of which we're going, 3-step process, pardon me, about how to go ahead and find this. step 1 is to find the derivative. Okay, step 2 is we're going to plug that x value, whatever that is, into the derivative and find our slope. And then use the point slope formula to go ahead and solve for the line. All right. So 3 simple steps there in that case, but again, of course, we need to put it in practicum. That's going to be fairly important. So let's go ahead and do that here in this instance. And let's use an example here as our good friend. All right. I'm going to pick a function here. I'll pick that function there from what I see in the book. So let's see here. So let's go with yeah, why not? We'll go with this one here. Just try something a little bit tougher. No, actually, I'll just try something a little bit easier. So let's try number 42 here. So minus 5/3 x squared plus 2x plus 2. All right. So minus 5/3 x squared plus 2x plus 2. And we're given the point here specifically at, let's go here, minus 1 comma minus 5/3. All right, fine. Okay, so that's what we have here. Minus 1 comma minus 5/3. We're trying to find the equation of the tangent line to that specific point. Okay, now let's go ahead and talk about each step here in succession. All right. So again, going back to our steps here really quickly. Oops, that's not what I want. Okay, so our first step here is to go ahead and find the derivative of the function. Let's do that first. So what is the derivative of f? Let's take a look at that first. So really quick here, what's the derivative of f according to this function that we have? What's the derivative of f here? Hey, Athena, how are you? How we doing tonight? Hopefully you're doing good. I'm sure you're getting a chance to sit and chill, have a nice time, maybe take in a little bit of extra math. Okay, maybe not, but maybe just sit and chill, hang out with me for a little while. Doing good. Finished some planting out in the patio. Ooh, it is nice weather, I ain't gonna lie. It's very nice weather there. Negative 10 third x plus 2. That is correct. Okay, so bring that 2 out here. We get negative 10 over 3 x plus 2. That's right. All right. Good stuff. Okay, so that's what you get when you plant stuff. You know, you gotta water it and take care of it. You know, my mom has a big old garden, you know, all around the house, and it's just like I don't even know how you even maintain half of that. It's just crazy. It's just flowers everywhere. Then the rabbits come by and they eat stuff. Then the chipmunks come by and they eat stuff. You know, and then we got some bird feeders and they come around, they eat stuff. Basically, everything they do, they come around and eat stuff. Mother Nature's got to got to roll on her own. All right, so let's go to step 2 here. Step 2 is we're going to plug in the x value of the point given into the derivative, and the resulting value will be our slope. So in this case here, this is the resulting x value that we're given here. We're given negative 1. The little shits. Oh my goodness. Yeah, especially chipmunks. They like to eat bulbs of plants. So they'll just like dig it out, and then once you like put some seeds in, they like to undig it out, and they like to eat them. And I'm like, ah, bruh. My mom and my sister like, yeah, why? You gotta plug that up with some some rocks or something. And I'm like, okay. Hey, this is the call of nature right there. Like as long as they're given an opportunity for food, they're gonna come around. Um, all right, so we're gonna plug in -1 here into the function. We're gonna have -10 thirds times -1 and add 2 to that. So if we do that here, we get 10 thirds plus 2. And so if you add those two together here, that's 3 over 3. That's going to be 6 over 3. So here we get 16 over 3. Okay, so 16 over 3 here is going to be the slope of our tangent line. All right, so if you need to write that down, give yourself a reminder here. This is the slope of the tangent line. Okay. All right. No problemo. All right. Okay, next. Let's go to step 3. So step 3 is again something of a, the only way was a scarecrow type things. I mean, you could build elaborate traps if you want to. I mean, it's totally up to you. I mean, maybe they have something like that. Like they have traps for mice and stuff. I don't know if they have humane traps for other critters. They probably do actually. In all honesty. All right, let's go to step number 3 here. All right, so step number 3 here says use the point slope formula using the slope found in step 2 and the point given and solve for y. All right, so here what you see on the screen is the point slope formula, which is y minus y1 equals m times x minus x1. Okay, so I want to point out at least one important thing here. Let's make things a little less confusing here, what you see here on the screen. That's your point slope formula here. Now on the paint tool here, we're going to make this x1 and y1. Okay, because what we're going to do is we're going to substitute in here the slope of the tangent line we found here in step 2, and this point that we're given here, that'd be x1 and y1. Yeah, I don't want to kill them either, obviously that's bad, but I don't know, some people do. Your neighborhood cats are pretty good for that. They're pretty territorial. They don't like things busting up in their territory. Admittingly, the neighborhood cats keep rodents at bay. So okay, so let's go ahead and do y minus y1 equals m times x minus x1. Okay, so we're going to replace stuff here for y1, m, and x1, okay? So again, be sure not to put anything in for y and x. So these are the only three things we're going to substitute in here. All right, so if you're not sure, just go a little bit slow and you should be all right. So here we're going to have y minus y1, which is -5/3. Again, put parentheses around what you substitute here. That's very important. Equals 16/3 times x minus x1, which is -1. Okay. Okay. Now let's clean up a little bit here. See what we get. So we get y plus 5/3 equals 16 over 3. And we have x minus -1, so that'll be x plus 1. Remember, it is important to clean up the problem here before you do anything else. Otherwise, usually sign changes and stuff get to be more confusing than they need to be. So now I'll distribute here the 16 over 3. So I'm going to have y plus 5/3 equals 16 over 3x plus 16 over 3. Then we'll just subtract by 5/3 on both sides. Then finally, we're going to get our final answer here. So what is our final answer? Sorry for the sudden transition. Our final answer here, if we're going to put it over here, will be y is equal to 16 over 3x plus 11 over 3. That's going to be our final answer to find the equation of the tangent line to that point that you see right there. All right, good. Are there any questions about that problem? Hopefully now that makes a little bit more sense. Makes sense? All right. Try to make it as straightforward as possible. It looks complicated. In reality, it's really not too bad. Hey, Ackle, good afternoon to you. Good afternoon / evening. Okay. All right. See here. Back to the here. All right. So let's take a look at some other problems here. Some whatchamacallit? Yeah, some application problems here, I should say. So go look at application problems. We'll go ahead and see exactly how some of this can work. It's really not as bad as it may seem. So it just depends here. All right, let's take a gander. Which one I want to do? Okay, here we go. All right, so we're going to do a particular problem here, and I want to kind of discuss about how that'll go. All right, so the next question here on the handout will be doing stuff with applications. So let's discuss about that here next. All right, and that's not what I wanted. Okay. So one of the applications here that we can do, and I'll come back to number 5 here shortly, but one of the applications that we can talk about here in section 3.1 talks about a particular application regarding physics, or more stuff in physics than anything else, which talks about relation of position, velocity, and acceleration of an object, or a dot, or whatever you want to call it. Now, the way we actually figure this out is actually doing it through derivatives. Now, what we have here is we may be given at the initial outset, we may be given a position function here. Usually that's called s of t. Okay, so s of t here refers to the position function here. Where would the position of a particle be on a flat plane or whatever? All right, if we take the derivative of that particular function, we get the velocity function. Okay, so what we have here is we take one derivative of s of t and we say, okay, that's going to be the velocity function. Yes, indeed, Athena. All right, thank you. And then finally, we have the acceleration function here. So the acceleration function here is going to be the derivative of the velocity function, or what we talk about here is the second derivative. So we have the first derivative, which is, say, the velocity, and then we have the second derivative, that is the second derivative of the position function here. A hydrate, yes. I got some still leftover coffee. All right. So that is how we go ahead and approach each one of those. I mean, it was iced coffee, but it still tastes good. I ain't gonna lie. Okay, so if we go back and take a look here at the example in the textbook, okay, here it says, let's do 59 here. So 59 says, during a test by the editors of an auto magazine, the distance S in feet traveled by a McPherson X2 racing car t seconds after its brakes were applied conformed to the rule here. S is equal to 120t minus 15t squared. All right, so let's go ahead and take a look here at this particular problem. And you'll notice that this problem here isn't as bad as it may seem once we understand the actual basic rules here of velocity and acceleration and position and all that jazz. Okay, so 59 here, we'll do S of t here. So S of t here is 120t minus 15t squared. Okay, all right. So what we want to do here first, we want to go ahead and find the car's velocity at any time. Essentially, they just want you to find v of t. All right, so using our rules here from our notes, we know that v of t here is equal to s prime of t. Again, just taking that derivative there of our initial function. So, can anybody tell me here, what is the derivative of this function? What's the derivative here? What is the derivative of s of t? What's that going to be? That derivative going 120 minus 30t. That is correct. Very good. So 120 minus, and then bringing that 2 out, 2 times 15, that'll be 30, and we'll have 1t left over. All right, great. That's correctly, Wen. Perfect. All right, so we found the velocity function here. That's what it asked us here for this first part. No problem. Easy peasy. All right. So let's take a look here at the next part of this question. All right, so the next part of this question asks, what was the car's velocity when the brakes were first applied? So when the brakes were first applied here, all right, what was the car's velocity? So all this is asking us for is basically saying, okay, what happens when t is equal to 0? So we're just trying to find a v of 0 here. Now, in all honesty, that's pretty easy. We're just going to take 120 times 30 times 0, pardon me. So that's going to equal straight up 120. Okay, so nothing too fancy going on there. There we go. All right. Let's take a good look here at letter C. What was the car's stopping distance for that particular test? What was the car's stopping distance for that particular test? So take a look at the hint that it says here. It says, okay, take the stopping time is found by setting v is equal to 0. All right. So if we set here the equation 120t, 120 minus 30t, just going to go ahead and set that equal to 0. We'll find out how much time it took for us to go ahead and stop this car. Okay, so we could go ahead and just we could just subtract by 120. Here you have 30t is equal to minus 120. Divide by negative 30. All right, and so here we get negative 120 over negative 30. And so here we're going to get 4 seconds. It takes 4 seconds to stop the car. It's actually pretty significant. So, all right, great. Any questions about that? I hope that one is pretty easy. Oh, pretty, hopefully relatively straightforward. It's not too bad. All right. Very good, very good. Would you guys like to try another problem? Yes? Okay, let's try another problem. That's fair. I always think it's important to take a look at a few more examples, but I have to ask first before I do in some cases. Okay. Um all right. Oh, that's actually interesting. Let's go ahead and do that question. That question's actually really really interesting. All right. Let's do 63 cuz 63 is a pretty valid question, at least a more common probably a question that does affect you kind of question. Reality question here. I mean, a lot of these applications are, but this one here actually hits close to home. All right, 63, consumer price index. An economy's consumer price index is described by the function here. I of t is equal to negative 0.2 t to the third plus 3t squared plus 100, where t is between 0 and 11. T equals 0 corresponds to the year 2003. At what rate was the CPI changing in 2008, in 2010, in 2013? All right, seems fair. Let's go ahead and take a look here. And we'll answer question B as well. We'll find the average rate of change, and then we'll also take a look at the rate that it was changing at both of those times. So in the first part here, at least discuss that. Now, for those of you who are not aware, the CPI is something that does affect you on a daily basis. The CPI is a statistic made up of, like, say, 60,000 goods and services or more made from the U.S. government to see what the change in prices are of those goods and services. Now, inflation is certainly something that has been on the mind of pretty much everybody these days. If you haven't been aware, inflation is kind of a big deal. Again, that means that if the higher inflation is, that means the more certain things will cost. Okay, um, maybe you haven't seen it, or if you have seen it before, um, again, for example, new car prices are very, very high at the moment. Okay, so if you see new car prices are pretty astronomical compared to other years because inflation is so rapid. So if we so if you take a look here, I can show you a little bit of a chart here to show you exactly what we're looking at. This is a chart of the current CPI. Okay, so the higher inflation goes, that means that the dollar here, your dollar is worth less at the end of the day. And you notice here at the very end of this graph, this is where we're at right now. According to this, inflation is close to 4 to 5%. All right, which is, well, needless to say, not great. All right, as you can see here, this was in 2008 when we last had a economy crisis. Inflation was pretty high, and then it had to bottom out because of the fact that the housing crisis happened, and then essentially we started to lose a lot more. Remember, though, during that time, a lot of people lost their jobs, and the economy was a mess for like a few years before it finally recovered. A few years later. So it took a while, but again, um, having too fast of inflation can be very dangerous. You want to keep it at certain levels so you don't mess up your own currency. And there have been cases where countries have messed up their currency in really nasty ways. So you don't want to have your money be worthless at the end of the day. That's one thing you have to be very careful about. So a great example of that is, I can see if I can find that here. There's actually, see if we can find this image here. There we go. You take a look at this image here. This was real currency at one time here. All right. This is for 100 trillion Zimbabwe dollars. Okay. This was a bill that actually existed for a period of time. Um, Obviously, yes, 100 trillion. If you ever wanted to be a trillionaire, you could just print it on a piece of paper, and there you go. Congratulations, you're a trillionaire. All right, now how much could this $100 trillion actually buy you? At the time, because inflation was millions of percent, because Zimbabwe's economy back then was completely out of control due to very poor policy decisions and food prices being set in stone. Um, yeah, you could probably buy, I don't know, a piece of bread for $100 trillion, or maybe a loaf of bread. It was that bad. It was really really awful. You can imagine that. You obviously don't want that to happen here. Things like this are currently happening in, say, Venezuela. Same idea, because of the current political turmoil. Then the economy has gone down as a result because of all that political turmoil. But again, then their currency is worth less and less over time, because then the value of that currency is just going to skyrocket. So you try and print as many bills as you can. Everybody thinks the way you make more money is just by printing the money out. It's like, well, that's not true. If you try and print a whole bunch of bills, your currency gets worthless over time. This has been tried and true for quite a long time. The Germans tried it after World War One. It didn't work out really well. Zimbabwe had the economic crisis. It didn't work out very well. They had to literally reset their currency. That's how bad it was. So yeah, it's one of those things that certainly has its definite applications, for sure. Actually, we could find out here about how much it costs for apparel. Wow, prices for apparel went up really high. Holy cow. Yeah. Education's been pretty standard. Shelter. See, here's new vehicles. New vehicles are on the rise. Um, Gasoline prices. I don't know if you've seen prices at the pump recently, but yeah, prices at the pump are pretty high. I think around here they're about 350. I don't know where they are at, what they are at in your area, but yeah, it's pretty high. So yeah, definitely certain things are highly affected by the CPI. So um, there's regular food, um, and then there's takeaway food. It hasn't gone up too much, but really some of the other things have gone up pretty fast. I was paying $25 for gas, and now today it was $40. Yep, that's right. And you want to know the roughest part? You want to know the roughest part about this? Okay. So there's a certain thing about this that people have to understand. That is that because inflation goes fast, if inflation goes up fast, you think about it this way. That extra $15 is essentially kind of like if I take money away from your pocket without having to reach inside your pocket. So think about it this way, right? Your purchasing power is the most important thing that you actually own. Okay? What you get with the money that you have is the most important thing that you should understand in business. How much can you stretch out your dollar? Okay? So, if you can stretch out your dollar pretty well, okay, then you're living well. It means that dollar is worth a whole lot more. But if that dollar gets you next to nothing, then you value it much less. Okay, so that's how we actually look at money here from a common sense perspective. If you talk to a person in San Francisco and say, hey, I make $25 an hour, they'll laugh in your face. If you come to the suburbs here of Chicago and you say, hey, I make $25 an hour, that's pretty decent. Okay, if you go to a booty town and be like, you know what, I make $25 an hour, that's pretty good. You really like where you're going. Okay. So the context does matter about the same $25 an hour and how far you can stretch it. That's what really matters. But the problem is that if inflation starts to outstrip how much you're making, well then essentially you're just getting money taken out of your pocket without me having to reach inside. The other issue is that rates for pay haven't changed that much in the past 10 years. So essentially, your purchasing power is being whittled down little by little by little without you actually without you having any choice about it at the end of the day. That's also a big uphill climb that a lot of people have to make. So that's something that you have to understand. That is something that is pretty evident for some of the things that are going on here in you know the current economic landscape. So for future generations, that's something that you have to act. That's the biggest uphill climb a lot of future generations actually have to shoulder the burden for. Is essentially um, how to stretch out their money and make it worth more because their purchasing power has been pretty much destroyed the past 10 years. um, Rates for pay haven't gone up with inflation. People are paying more for rent, but you're still making the same amount of money as you would 10 years ago. That makes no sense. So it's very, very difficult right now for a lot of people because of that fact. That's why you have a big divide between the haves and the have nots. So a lot of that was little by little, but then it becomes a big deal once you see the big picture. It's a good way to kind of describe it. All right. In any case, I digress. All right. But let's go ahead and do this here. We said what's the rate that it's changing here in 2008? Okay, well let's take a look here. We want to go ahead and find the derivative of this function. So let's put down this function here. Okay. The so let's put down our function. Oh man, give me a second here. I need to get rid of this. All right, so we have a function here of I of t here. We're representing this function here. So we have negative 0.2 t t to the third, okay, plus 3t squared plus 100. Okay, so we have t here is again t equals 0 represents the year 2003. Okay, so 2003. All right, so in letter A here, let's find the derivative. All right, so the derivative here should be pretty easy. If you have figured out the derivative here, is going to be negative 0.6 t squared plus 6t. Okay, so that is the derivative here in this case. Now it does ask us three separate parts here. We'll do just one. That's perfectly fine. Well, how fast is it changing in 2008? Okay, what does t equal to in 2008? If we want to plug in a number here, what should t equal to if it's the year 2008? what should we have here? 2008 represents what value for t? It represents 5. Okay, very nice, Emma. That's correct. Good. So we're going to plug in 5 into our function here. All right, and let's see what we get here, right? All right, good, good, good. Check that really fast. That's okay. We're fine. We're fine. All right. All right. Oh, I messed that up. So here we're just going to plug in 5 to represent 2008. Again, you can plug this into the calculator. Shouldn't have any issue. So we have negative 0.6 times 25 plus 30. And go ahead and do that out. So here we get 15. Okay, so 15 is what we get here for 2008. All right. Good stuff. All right. Any questions about that so far? Hopefully that one's not too bad. We're just going to do one of those 3 parts there, but you're pretty much just plopping in numbers once you got the derivative going. All right. Letter B here should be a reminder from what we did here last time. So letter B here says, now note the difference here in the wording. I want to point this out here. Letter B asks, what was the average rate of increase in the CPI over the period from 2008 to 2013? Now the key thing here is the average rate of increase, okay? This talks about the average rate of increase. So does anybody remember here what did we use here for the average rate of change? Well, we used a particular formula here for the average rate of change. What is that? What's that going to be? Anybody remember that little formula there? And this one here may be a little bit tough, but talked about it a little bit yesterday, so see if you remember. If not, that's fine. All right. Well, if you're not sure, that's okay. So if you remember this, the average rate of increase here, we're going to use this formula right here. We have f of b minus f of a over b minus a. We're going to go ahead and use this formula here. Now, in our case, we're going from 2008 to 2013. So we would have 5 here to represent 2008 and 10 here to represent 2013. And we were going to go ahead and use the original function here to find out what that average rate of increase is going to be. So we have f of, so again, our a here would be 5, our b here would be 10. So we have f of 10. Yeah, exactly, Lewin. There you go. So here you got f of 10 minus f of 5 over 10 minus 5. Okay. And so here we're just going to plug in 10 and 5 into our function here. So let's go ahead and see what we get here. Again, if we need to, let's go ahead and do f of 10. This is just strictly calculator stuff here from here on out. So 0.2 times 10 to the third. Again, we're not using the derivative here. We're using the straight up original function. Okay. All right, so 10 to the third is 1,000. 1,000 times 0.2, well, that's like minus 200. So then that's going to be 100, that's 300, so that's 100, that's 200. Okay. So f of 10 here will be 200. All right, f of 5 here. Let's go ahead and just write this down here. Reminder. All right, 3 times 5 squared. That's going to be 75 there. Get 100. I get 125. So if I get 125, that's minus 25. That's going to be 50. That's going to be 150. All right. Again, you could use the calculator for this, but you'll get these two results to work out. So you can get 200 minus 150 divided by 5. So we go 50 divided by 5, and so here we get 10. Okay, so there we go. We got our values here for this one. All right, and that's all we got to do. Good stuff. All right, questions? Questions so far? I'll let you take your time with that one. It's fine. I'll bring that back up again if you're sure about that. No? Okay. Perfectly fine. Okay. Let's take a good look here at the next one. All right, so I didn't do number 5 here, but technically you can easily do this here. Is again, what is the sum and difference rules here for derivatives? All right, so the sum and difference rules here for derivatives is basically if we add two functions together, you could just basically take them apart and do the derivative of each individual function here. So f plus g prime of x is equal to f prime of x plus g prime of x. So you could just split it apart if you want to, if you have two separate functions. And we've done this a few times now when we just take each term and we just do the derivative. Same thing with subtraction here. You can just split it apart and just take each individual derivative and slap it together. It's really not too hard. Now, there's not many examples here because pretty much every example is going to be something akin to what we did here in this last example, where it's just like a string of terms put into a function and then just taking the derivative straight up. So at least for plus or minus, it's very straightforward. You don't have to do much. It's not anything different than what you've done before. There it is. It's very straightforward. All right, but what we're going to be looking at here next is going to be a different take on the other two operators, which is going to be multiplication and division of fractions and taking those respective derivatives. We do have two different new rules that we want to go ahead and look at. Now, before I go ahead and get started with that here, it is approximately 6:53. But I want to ask here, very first and foremost, if you would like to take a break, because that was something that I didn't do last time. So this time I am going to ask. If you'd like to take a 10-minute break now, we could take a 10-minute break now, or we can continue moving forward here. Yes, take a break. Okay, that's perfectly fine. All right, so if we're going to, yeah, not a problem. I know that's a lot of information dump. Totally understand. So let's take a 10-minute break here. We're going to come back at 7:05. All right. Let's come back at 7:05. All right. And we'll take a small break here, and then we'll resume here, starting off with section 3.2, talking about the product and quotient rules. All right. Let's go ahead and do that.
pushing our best, you're all we get. You made it all this way, cause you couldn't stay happy with the way we're going on. Hey, you have got to say, we're in the wrong. Worthless jealousy, you will never be going back to your broken world. Get lost if you can,
Okay. All right, let's get back to work here. It's 7:05. Hopefully, get a chance to decompress a little bit. All right, we are back. All right, let's continue moving forward here with some new material. So, hopefully, everybody is back and ready to go. All right, we're going to go ahead and get moving here with the next section, which is section 3.2. We're going to be working a little bit more with derivatives, only this time we're going to be working with the last two options here for derivatives is what happens when we multiply functions here together and what happens if we divide functions. Okay, so we have the product rule and the quotient rule here. And so I'm going to leave this up on screen. I'm actually going to make this smaller here. Yeah. That didn't work out the way I wanted to. Fine. All right. There we are. Okay, so I'm going to go to the screen here. Okay. So what we have here specifically is let's talk about the product rule here of derivatives first and foremost. As you can see here on the screen to the right is what is the product rule of derivatives. Now the product rule is if we multiplied two functions here together, f and g, and we said, okay, well, what's the derivative of that particular function? So we say a derivative with respect to x, that's what the d over dx thing represents, of f times g is equal to f either the derivative of f, or f prime of x times g of x, plus the derivative of g, which is g prime of x times f of x. Or an easier way to kind of say this is, and you'll often hear me say this quite often, is that's going to equal f prime g plus g prime f. Okay, so probably one of the easiest ways to kind of rattle it off really easy is f prime g plus g prime f. So kind of leaving off the x's there, and that's perfectly fine. Now, this can certainly occur here in several cases. Let's take a look here on how we can go ahead and approach this here when it comes to doing certain functions. So let's look at some examples. Okay, using this product rule here. We'll go to the textbook here. All right, here we go. Okay, so let's look at these first batch of functions that you see here, and we're going to do this on the paint tool here. Oh, down here again. All right, and we're going to apply the product rule here. So let's try, without foiling. We're not going to foil it, but we're just going to go ahead and just see what we get here. So let's try. Actually, I'll just make one up here because it's going to be similar to that anyway. So let's try this here. Let's try x to the third minus 2x squared plus 3x minus 1. We want to multiply that by x squared. Let's call it 5x squared minus 10x plus 27. Okay. So let's say we have these two functions here we're trying to find the derivative of. We'll call this h of x. Okay. All right. So let's go ahead and at least define that here. All right, here we go. Okay. So what's the trick behind this? Well, again, the trick is just we're going to use this rule here of f prime g plus g prime f. So in order for us to go ahead and do this here, again, just go ahead and label f and g. I said, why not? So just underline it. That we call this first function f. And then the second one here, we call this second function g. I said, okay, cool. All right. So just label f and g here and then apply the rule. So let's at least look at each one here, okay? So let's look at f prime. Let's figure out what that is. We'll also figure out what g prime is. And we'll put it together here using the rule that we got here. And you got yourself a winner. Winner chicken dinner. All right. So what is f prime going to be here? What's the derivative of that first function we see there? What's the derivative of that function going to be? Wait, tell me, what's the derivative of x to the third minus 2x squared plus 3x minus 1? Let's see here. Hopefully we get it. What is the derivative of f? Right, 3x squared minus 4x plus 3. Okay, that is correct. Okay, good. All right, that is definitely true. That is definitely the derivative of f. Very good. And we're going to come back to this here in just a second. But let's figure out what's the derivative of g. So what is derivative of g? (10x minus 10). That is correct. Yes. Okay. So now all we have to do here is put 2 and 2 together using the rules that we have here. So we have f prime g. So if we're trying to find the derivative here of h of x, okay, we're going to use f prime g. So f prime g is equal to g prime f. Okay, so first going to have f prime g. So 3x squared minus 4x plus 3 times g, which is 10x minus 10. And then we'll have the plus g prime f part here. So bring up the plus here. So again, we'll have, oh, oops, I meant to put, sorry, my bad on that one. I meant to put g of x here. Sorry, I accidentally put both of them at the same time. I meant to put g here. Be the 5x squared plus minus 10x plus 2. Come on, stop being dumb myself. All right, be helpful if I wasn't so dumb. All right. So we got f prime g plus g prime f, so that'll be the 10x minus 10. And then we put in f, the original function here, which is x to the third minus 2x squared plus 3x minus 1. And this would be your final answer for this particular problem. Again, if you wanted to, you can go ahead and FOIL it out. Again, it's pretty long and ugly, as you can probably tell if you wanted to FOIL stuff out here. But yeah, that's pretty much how you do that particular problem there in that case. All right. Any questions about that so far? Let's go ahead and try another here. Now that you have a pretty good idea about what the expectation is. Which one I want to do next? Not that one. That one's not ready yet. So, all right, let's try this one here. So, something with a root in it sounds good. Let's say we have, let's see, S, call it B, and we'll call it B of X. Say it's equal to 1 plus root T, 1 plus root X, sorry, and then 2x squared minus 3. Fine. All right, seems fair. Okay, again, we're just going to go over F and G here. Again, underline F and underline G. All right, so that's the first thing that you should do here in these problems is just organize your thoughts. make sure you have that organized and set and ready to go. All right. So here we're just going to go ahead and find out what b prime of x is going to be. So again, that's going to be f prime g plus g prime f. And because we're using the product rule here. So let's find out what f prime g, what f and g are in terms of its respective derivatives. All right, let's take a look at the derivative of f. What is the derivative of f in this this thing? What is the derivative of f? Get here, the derivative of f. Negative 1/2 x to the minus 3/2. I agree. Not quite. Not quite in this case. You have the square root of x here. So again, you can write that as 1 plus x to the 1/2. So you have the right idea there, Elizabeth. It's not the just not the right numbers there. Yeah, it's not negative because it's in the numerator. So you have just straight up square root of x, right? So that's going to be x to the 1/2. Straight up x to the positive 1/2. If it was 1 over x to the 1/2, that would be x to the negative 1/2. I would agree with you 100%. That's if I had 1 over that. But that is not what I have here. So if I had this, right, if I had 1 over the square root of x, then I would agree that's the derivative, because this is x to the minus 1/2. That's the fundamental difference between those two. So having said that here, what do we get for that? Almost, not quite there. Okay, I'll wait. I think you're almost there. Okay, there we go. Now you got it. 1/2 x to the minus 1/2 is correct. Good. That is correct. Very good. All right. Yeah, just putting that together, kind of a couple pieces there. There you go. What about my man? It's okay. It's okay. You thought it was one way, and in reality, it was the other. So it's just kind of like slowly putting the pieces together. All right. How about g prime? I think that'll be easier. So how about the derivative of g? What is the derivative of g? All right. 4x. Okay, so a lot easier here for that. 4x is correct. Okay, so simple. Put my money on it this time. I like your odds there. Better than roulette. All right, good. All right, so let's put our definition here together. F prime g plus g prime f. So what we get here, what we're going to get here for our result is we're going to get f prime. That's going to be 1/2 x to the minus 1/2 f prime g. So g here from 2x squared minus 3. And then plus g prime f. So we have g prime here to be 4x. And then the latter half here of this is going to be specifically g prime f. So that'll be 1 plus root x. And then that is what we get here for this problem. All right. Good, good. Okay, questions so far about the product rule. Any questions about the product rule? So like I said, the shorter way of just kind of saying it, it makes it a tad bit easier to do. Okay. Alrighty. Well, let's take a look here at the next part. Can I pull the word? Yeah, sure. Not a problem. Seems you guys are coming in delayed. I don't know why you guys are a little bit more delayed than usual. So I'm looking at my stats, and you guys should be like on a 2 second delay. But I don't know if it's coming in like 5 or 6 seconds after I say something. I know there's always a few seconds of delay. So let me know when once you got the work down there, Nick, and I'll move forward. Got it? Okay, perfect. All right. Let's go ahead and look here at the next part here. All right. So let's move down here to the next part. Let's talk about the quotient rule. All right. So the quotient rule here is basically going to be taking the derivative of division of two functions here. Now, it is different here, slightly different here than that of the product rule. So let's take a look here at what the definition here with x is. Again, that's going to be f prime of x times g of x minus g prime of x times f of x all over g of x quantity squared. So to put it into shorter paraphrasing form, it'll be f prime g minus g prime f over g squared. Okay, that is what the quotient rule will say here in this case. All right, so f prime g minus g prime f. The product rule here was f prime g plus g prime f. This one here is f prime g minus g prime f. And then all over g squared here is the rule for the quotient rule here for derivatives. So let's go ahead and practice with that here as well for some functions, and we'll see how things will work out. Okay, so that's not a very interesting function. Let's do another that doesn't absolutely smell. Yeah, that one's okay. All right, I can work with that. Oh, that's me. That one. That one's a little bit out of the purview. All right, a little bit out of the purview. All right. So let's do this one here. We'll have another h of x, and we'll have that equal to, well, how about the one you see there on the side? Go with x plus 1 over 2x squared plus 2x plus 3. All right. Again, just as before here, let's label f and g. We have f is the numerator, g is the denominator. Okay, again, you should put these in order here. That should be pretty obvious. But again, just making sure that got that down. All right. In any case, let's find out what f prime is and g prime, and then we'll plug it in to the formula here. Again, that's f prime g minus g prime f over g squared, all over g squared. So we're going to certainly have that there. All right. So can anybody tell me here, what is the derivative of f? What's the derivative of f? What's the derivative of f here? What do we get? One. That's correct. Very good. The derivative of f is indeed 1, right? Because we have x there, and the derivative of x is 1. Oh, good. Okay, good. We learned a little bit from yesterday. I know that it was a little rough go there, but yeah, 1 is correct for that. Perfect. What's the derivative of g? Uh, derivative of g is 2. Oh. Hmm. You didn't make me worry there. I was worried there for a second, Elizabeth. I'm like, wait, what? Oh, you're looking at the formula. Why? All right, that's fair. 4x plus 2 is correct. Good. We've reached the peak insanity level. All right, so I'm glad we've made it. We've made it, ladies and gentlemen, to the peak sanity levels. All right. Um. All right. So let's go ahead and plug it in. We'll do f prime g plus g prime f. So f prime here is 1 times g. So that's 2x squared plus 2x plus 3 minus g prime, which is 4x plus 2. Okay. Times x plus 1, which is f. And all that's going to be over g squared. So we have 2x squared plus 2x plus 3. All right. And we're going to square that, of course. There we go. And that's it. That is going to be our answer there. You can simplify it if you like, but I usually leave it a little bit unsimplified. But there you go. You got it. And that's the answer to that question. Excelente. All right, let's go ahead and try another here. I think another one is in order. Again, if you have any questions, please let me know. All right. Okay, so let's go ahead and put in another function here. Which one looks decent? I want to do. Oh, that one's actually really good. All right. This one here is actually a really good problem. So let's do that one. X plus 1. Okay. So let's take a good look here at this one. All right. This is our function. Again, we have our functions here, f and g. We have f on the numerator. We have g in the denominator. So let's figure out what f prime is going to be here. And g prime, of course. All right, so let's look at the derivative of f. All right, so here at the top of f, for f, we have x plus 1 times x squared plus 1. What's the derivative of f here in this case? What is the derivative of f? Actually, maybe I should ask a better question. What should we do in order to find the derivative of f here? What should we do here to find the derivative of f in this particular problem? You can distribute. All right, so there's a few options. Distribute is one of them. I agree. Can we find the derivative of both parentheses and then multiply them together, or do we have to multiply them first? Well, we can't do that. There is a reason why we cannot just find the derivative of both parentheses and then multiply them together. Now, I agree with Emma's suggestion where you can distribute here and then FOIL stuff out. That's actually not too hard. What's another alternative that you can do here? You're kind of on the right track there, Elizabeth, for the second option, but it doesn't quite work that way. What else can you do here? So distributing is one option available to us, at least in this problem. Not available in every problem, but in this one, yes, I agree. But there's a second option on the table that we haven't considered yet. What's that second option here? This one, again, the reason why this problem is really good is because of this second possible option. Because it's a pretty realistic option in all honesty. So I want to go back here for just a moment. What's a possible second option here? That's the real crux of this question here, and that's what's going to make it a little bit tough here at first, because some functions can fall underneath this category. But if you understand that you can do more than one thing, then you'll see that this opens up a lot of different pathways. Anybody have any idea? Let's take a look. Let's see if somebody can figure that out. Why don't you take a look at F here? If you take a look at F, I know it's a little confusing, totally confusing. I totally agree. It is confusing. But take a look at F carefully. Don't you have something multiplied by something, right? Don't you have like two things multiplied by each other that you want to take the derivative of, right? What rule could you use here in order to find that derivative? For just the numerator part, just look at the numerator. Just look at the top part there. What rule did we just talk about here if we're going to find the derivative in this case? I guarantee you it's right there on the screen. I'm looking right at it, sort of, question mark. What rule can we use here to find the derivative of f? This is actually pretty important to know because some problems actually have this in there. So again, you can combine rules here, by the way. It is not limited to just using one rule just necessarily. You can have a rule within a rule here. It's actually going to be important for the next section for sure. So I know this is going to be tough. Uh-oh. Things are ground to a halt. Looks like everybody is lost. Oh no. All right. So what is the answer to this here? The answer to this here, very important. I'll put this as a note because we've had a lot of issues with this now. Is the product rule in the quotient rule? Hey, all right. You got it. All right. I was worried for a second. Well, worried for 5 seconds. Okay, maybe 5 minutes. So note here is that you can use rules within rules here. Note. You can use rules within rules for derivatives. So in this case here, you can use, in order to get f to work out for this, okay, to solve for f, you need to use the product rule for the numerator. So that's the big key here in this case, is you have to use the product rule. If it's like super complicated functions, and you have to use the product rule. So distribution here is something you can do, and I'm not denying that at all. That's absolutely correct. All right. But let's say they were two messy functions, and you had to say, well, foiling them together is going to be pretty much a disaster. So it's like, well, how do I go ahead and avoid that? Well, using the product rule here is actually appropriate. So I'm going to use the product rule for f. So here, if you want to break down your two functions here, this is kind of like your first guy. This is like your mini f, and then this is like your mini g here. And then all you're doing is applying that same exact rule here. And this is how you get the actual derivative. So the actual derivative here will be, and I'll quickly do this here, derivative of f is 1, so f prime g plus g prime, which is 2x, times f. All right, so f prime g plus g prime f is how we can go ahead and find out what f prime is going to be here. Again, what the derivative of the numerator is going to be in this particular case. A g prime here is pretty easy. That's just going to be 1 straight up. But the important part here that I do want to stress is, again, a rule within a rule here is not off limits. Okay, in fact, it's something that we're going to exploit quite a bit here. We're going to exploit that quite a bit here, especially in the next section. So having this around certainly as something good to remember is going to be very, very helpful. And now we just put the pieces together using our rule here for the quotient rule. Again, f prime g minus g prime f over g squared. And so if we put this together here, we have f prime g. So let's go ahead and put this down. We have, I need to zoom out here a bit because I need the room. That bit. Okay, so we got f prime, so that's going to be 1 times x squared plus 1 plus 2x times x plus 1. So that's f prime times g, which is x squared plus 1, which is x minus 2, sorry. Looking at the wrong thing. Right? And then minus a little bit more there. Minus g prime f, so minus minus 1 times f, which is that whole thing that you see on top. So this x plus 1 times x squared plus 1. And then this is all this thing is going to be over g squared. So this is going to be over x, what is g? X minus 2. So this is the derivative here of our function. Again, if you need to clean this up, you can clean this up here. But I'm just showing off here that, yes, a rule within a rule here is definitely not out of bounds. Right? It is entirely a plausibility. Okay, are there any questions about this particular problem? Okay. I want to be sure that everybody's on the same page about this one here. because I feel that this is probably the most confusing one here. If you had a tough time with this particular question, again, that's okay. Try and get a little bit of practice in. That's not a big deal. So I want to take a look here at some other guys. Okay. I think we'll do that for then. So that's okay. All right. Good stuff. Okay. Now everything else here pretty much works the same. I'll go ahead and do one of these problems here really quick as a quick example here, but pretty much the application problems are going to be just using the rules there of product or quotient rule and just kind of plugging in numbers here. One of the problems that is applicable here, we'll look at 46. So it says find the equation of the tangent line to the graph of the function here. Since we've already worked on this here today, let's go ahead and at least do 46 here together, and we'll see exactly how that mets out. But you'll see that the process here about how to find the equation of a tangent line, regardless of the circumstance that you work with, is going to be exactly the same. Find that derivative, go ahead and plop in that point, okay, and then you're like, well, okay, what's the slope? You'll get the slope and then use the point slope formula. Bada bing, bada boom. So here for 46, make that a bit. Here for 46, again, we have our function here of 3x over x squared minus 2. And we have the point here of 2 comma 3. Again, we're going to use the quotient rule here. So this will be like our f on the top. This will be our g on the bottom. So again, we have f prime g minus g prime f over g squared. Again, if we do f prime, that's going to be 3. If we do g prime here, that's going to be 2x. So if we do this out here really quick, we get 3 times x squared minus 2 minus g prime, which is 2x, times f, which is 3x, all over x squared minus 2 quantity squared. Okay, so this is the derivative that we have here. Now, since we're given a point here of 2 comma 3, again, we're going to plop in this 2 here in for every x in our derivative to find our slope. So if we plop it in here, we find out what f prime of 2, we find out what 2 is here when we plop it in. So let's see what happens with Ploppingtons. All right, so here we get 3 times negative 2 squared minus 2 minus 2 times negative 2. That's kind of for 2x here. And then we have 3x here, so we have 3 times negative 2 all over negative 2 quantity squared minus 2, and then we square that result. All right. So this is what happens when we plug in minus 2 into this particular problem. Let's clean this up a bit so we can see what numbers we're working with for this slope. Negative 2 squared is 4, so we have actually 4 minus 2 here. Minus negative 4 times negative 6. And then on the bottom here, we have 4 minus 2 quantity squared. All right. All right, let's see what we get here after we clean this up even more. Even more cleanup here. So this is 3 times 2. Minus 4 minus 6, that's minus 24. Over 2 squared. Or again, we get 6 minus 24 over 4. That's going to be negative 18 over 4, or negative 9 halves. So negative 9 over 2, after all that little busy work there for the numbers, is going to be our slope of our tangent line. Okay, so this is our slope. We also have a point here in this particular case, 2 comma 3, which will be our x1 and y1 here. That zoom awful. How to do? Okay. Okay. So negative 9 halves. Pardon me. Let's put that over here. For some reason, pretty bad. So, and we have 2 comma 3 here as our x1 and y1. So let's at least take stock here at that. Okie dokie. All right. So we're going to use our point slope formula here. So y minus y1 equals m times x minus x1. Our number, wow. It's like 2 hours of water for plants. Oof. Big oof. Talk about pet project for real. So here you have y minus y1, which is 3, which is m here. M is going to be our negative 9 halves. X minus x1 here, which is 2. So here we get y minus 3 equals negative 9 halves times x minus 2. If we do this out here, let's make this big screen here. If we do this out here, we're going to get y minus 3 equals negative 9 halves x. Negative 9 halves times negative 2 is going to be plus 9. 1 hour, it's a lot of water. That's a lot of water, Athena. I'm going to add 3 to this. So we're going to get our final result here of y is equal to negative 9 halves x plus 12. So there we go. Did a little bit of work here, but now we found the equation of the tangent line here. Again, in this case here, using the quotient rule to find our derivative, plopping in the number. Same process here. Again, just using one separate rule here for the quotient rule, but really the rest of the process here is no different from before. Just finding the derivative is slightly different, but it's just using another rule. So no big deal. Good thing I don't pay the water bill. Not yet. Not yet, anyway. Not yet. All right. All right. Very good. Are there any questions about this example here? Any questions at all? Fair enough. Any questions about today's lesson? No? Okay. Let me know if you want me to keep this work up here. That's perfectly fine. All right. Hopefully I went. Hopefully I didn't go too fast there. Hopefully I went slower enough to kind of follow along there. And I just kind of had to rush that last example since we're running out of time. But want to be sure that everybody is on the up and up there. So, okay. Well, that works. All right. if there are no more questions here, I want to thank everybody for coming on out here to the stream once again here today. Thank you very much, everybody, for coming on out. It's very, very kind of you. I know that the material here can be a bit heavy at times. But again, I want to be sure that everybody understands at least some of the material here can be a little rough to deal with, but hopefully you've been able to work with it without too much trouble. So just just let me know. Just let me know if I'm going too fast at times. If you guys have questions, I know you guys are mainly quiet, but please ask me anything that you guys want. Okay, again, I'm here for you. All right. So if you don't want to listen to my my face talk, for 2 hours, feel free to just interrupt me. Say, hey, can you explain that again? Or, hey, can you go over another one? Or whatever the case may be, okay? So just tell me. Just let me know, okay? Again, I'm not here for myself. I'm here for you, okay? And to help you understand how kind of the basic calculus is going to work with some business applications. All right? Thank you, Athena. You too. I'll try and stay cool as cool as possible. Kind of glad I didn't take algebra. Well, this is more business calc side, so it's a little bit different than algebra. It has some algebra in it, but of course, but a few more rules, of course, associated with that. But yeah, as I was saying here, again, feel free to stop me about whatever. I don't mind. Okay, it doesn't matter. Again, just again, participate here. Just talk. I like hearing from you and just saying, hey, I want to see. I just basically the reason why I ask so many questions is just to gauge your understanding, okay? And if you're having trouble understanding something or anything like that, don't feel ashamed. I'm here. I'm not here to make fun of you. I'm here to help you be better, okay? So if you're having trouble for whatever reason, please just let me know, okay? I'm not your enemy here. I'm just trying to reach out to having a helping hand. All right? So yeah, just to give you a friendly reminder about that. So I'm not here to admonish you or anything like that. I'm just here to just be sure that we got stuff down and we have a full understanding about what this material is talking about. I know it's 6 o'clock to 8 o'clock. I know people tend to be tired and stuff. So so you just come here to annoy me. So yeah, just feel free to ask me whatever. I'm always here to answer your questions. Email me if you're having trouble. Okay, don't feel embarrassed. I'm not, like I said, I'm not here to make you feel embarrassed. I'm here to help you. All right. Okay. Thank you so much here for coming on out here to another class. We're gonna be right back here tomorrow. We have possibly a couple more sections to do. We're gonna start on the next section here. Section 3.3, we're going to talk about probably, in my estimation, probably one of the most important rules in this entire course. So we're going to spend a lot of time on that because I'll give you a fair warning here. The next section here, at least the next question on section 3.3, is probably going to be the largest crux of the course. If you don't, this is like one of the concepts here where I say, this is kind of like hey, you got to understand this, otherwise it's going to have a very rough go. Okay, so I'm going to spend a lot of time on that so we can get that down as best as possible. And of course, some applications associated with actually applying that. Of course, we have stuff to do with that. So certainly another derivative rule, but probably in my estimation, the most important derivative rule, apart from, of course, the ones we've already looked at. So we'll look at that in section 3.3 there. All right. Thank you again, everybody, for coming on out. I love you all. We will see you all tomorrow here. Take care of yourselves. Again, feel free to email me or put me on Discord. That's fine if you need help. And we will see you then. All right? Thanks, Athena. Appreciate that. Thank you, Alex. Thank you, Elizabeth. Thank you, Emma. Thank you, Ackle. Thank you, Li Wen. All right. Thank you, everyone here. We'll see you tomorrow. Take care of yourselves, everybody. All right. Bye.